Hi everyone. So I wanted to go over discussion 3, particularly questions 2 and 3, because I feel like in discussion we didn't have enough time to go over them in detail. I wanted to talk specifically about how I would approach these problems and how I can check that, given that I write some code, that it actually makes sense and that we can kind of double check our work. First off, we have question 2, which deals with singly linked lists. A singly linked list is this S node. Well, it's two classes. First is this S node, and there's also this SList down here. So what this really means is that there's this wrapper class called SList, which has this variable called head. And this variable points to an S node, and if you look at the class right here, an S node just has two attributes. One is called val and one is called next. The val holds some number, for example 5. A double is a type that represents a number. And the next points to another S node. For example, I have an S node here which has 6 as the val, and since S node is an object, all containers that can contain objects can also point to null, so I can say that this particular S node actually points to the null. Now if you look at this part, this looks exactly like an int list from last week. This new part is just this SList wrapper class, and we'll find out that wrapper classes make our lives easier when we want to, for example, mutate the inside of our data structure, our linked list here. So given our example, this gives us some stuff to work on. We want to write insert. So given the following structure for a singly linked list, write a method to insert elements into the given position. If the position is invalid, insert the new node at the end of the list. For example, if the SList is 5, 6, 2, insert 10, 1 would result in 5, 10, 6, 2. Now we can unpack this some more in our picture we have above. In this case, let's add the 2 in. So for example, pretend like this actually pointed to the 2 to begin with. Now if we want to insert 10 at position 1, what we want to do in Java is to create a new SList node that we can put 10 in as the val and insert it at the right position. If we look and index into these SList nodes, these S nodes, we know that the first box will actually be position 0, the second box will be position 1, and the third box will be position 2. This means that if we want to insert into position 1, we actually have to create a new box here with 10 in it, and somehow we have to modify the arrow so that instead of pointing to the box with 6 in it, this box with 5 in it will point to this new blue box. And the blue box's next will point to the old position 1 box with 6 in it. So moving on, how do we actually start writing code for this? Well, if we look at the example, this is SList with actual elements in it, but nothing says that head actually has to point to some objects. Head could very easily just point to null, for example like this, which means that when we're writing code for this, actually have to check for that. Now for question 2, I'm just going to pull up the example, or rather the solution, because we covered it a little bit in section. If we start out right here and we look at this blue section here, it says if head is equal to null, or if position is equal to 0, then say head is equal to S node of val and null. Now the first thing we want to consider is head is equal to null. This is illustrated by our example up here. Basically, if we don't have any nodes to begin with, or if we want to insert at the very beginning of our list, if position is equal to 0, then we say that the head of this, that attribute in SList is equal to a new box whose first value is val and whose second value is null. So for example, if we want to insert at position 0, 1, then we would create a new box whose first value is val, in this case 1, whose second value is null, and we say head now points to it. And that's why that code exists. However, we also have to consider the general case. Let's just continue with the example we have on the discussion. It says to insert 10 into position 1. Now, the way you might approach this is first we have to get to position 1. and then we want to insert the 10. So there's two components to this. We have to somehow iterate through this list until we get to the right position, and then we'll create this new box where we can do the insertion. Let's just go ahead and take a look at the code. If you look, we have some pointer called cur, which points to our head, and it says while position is greater than 1 and cur.next is not equal to null, position minus minus cur equals cur.next. This part itself describes this idea of iterating through the list. If we go through our original example, we want to say that cur is equal to head. In this case, cur would point to the current head, which is this box with 5 in it. And then we go into the while loop and we said while position is greater than 1 and cur.next is not equal to null. In our current example, position is already 1, so we don't actually have to go through the while loop. But if we had, this is really checking to see if we have gone to the right position and we haven't run out of list. Both of these things have to be true in order to continue in the while loop and do this position minus minus and cur is equal to cur.next. The reason why we want to do this because that actually allows us to iterate through the list. And this check is saying I want to get to the node right before the position I want to insert, and I want to make sure that I haven't run out of list yet, right? It says here that if the position is invalid, which means if the position is greater than the length of the list, insert the node at the end of the list. So either one of these positions, either one of these clauses being false will kick us out of the while loop. Now moving on, the actual insertion gets done by this code. It says first we want to remember what the old cur.next is, right? Assuming that cur.next is in the position that we need, the one right before the position that we want to insert in. And given that, we can say that the next is now a new node whose first value is val and whose second value is the old cur.next. So if we're trying to insert into position 1 this number 10, we don't actually go through the while loop because the position given our list here would be already equal to 1, so that doesn't hold true. That means we automatically skip this while loop and we go straight to this code here. If we go back to the picture, that means that temp is equal to cur.next, and then we create a new node called, well, it isn't called anything. It holds our val though, so it's the box with 10 in it, and it's equal to whatever temp points to, the next value that is. And then we say that the current cur, right, points to that box. So the real big components of this code was the getting to the place where we want to insert and then doing the actual insertion, as denoted by these two sections here. If you draw out some box and pointer diagrams, which I strongly encourage you to do, you can play around with some bigger examples and figure out how exactly this code works step by step and how each line corresponds to that step. Moving on, question 3 asks us to do the same thing except on a Sentinel node. This I'll actually do using just writing our code from scratch. We already covered this question 2 in discussion, so I just kind of pulled out the old solution. But first we have to figure out what Sentinel nodes are all about. So Sentinel nodes are a way to make our code a little bit easier to understand by making our data structure a little bit more complicated. It's only a little bit more complicated because the Sentinel SList is a wrapper class which works exactly like SList, except instead of keeping one pointer to some S node, it keeps 2 pointers. And at the beginning, these 2 pointers point to SLists, or rather S nodes, that are just kind of there and not really real values in our S list. These 2 nodes are the Sentinel nodes. They're dummy nodes. They don't actually have any real values inside. And the reason why we want to do this is that writing the code will actually be a little bit more straightforward in the long run. If you looked at the previous code we had, the weird part of this was that there was kind of a if check to make sure that the head wasn't actually null. Now we're going to get rid of this if-else statement altogether because we had the sentinel node. So again, I'm just going to go and kind of come up with an example of a sentinel node, or rather a sentinel SList, so that we actually can see what this looks like when we have real values inside. So I'm going to draw the sentinel nodes in blue here. They have zeros. They're not particularly important except to literally take up space. Oops. And the head sentinel node will point to the its next will point to some values, right? Some S node which have the actual values. And then the last real node that contains a real value points to the back, which is some dummy node in blue. Now, just like before, we wanted to insert into the, an SList like this. Notice I'm using examples a lot. It really helps my thinking, at least. I think at the beginning it might help yours too. Let's say we want to insert the number 42 into position 2. So given that we have this example here, we want to count our positions. This is position 1, this is position, no, rather, this is position 0, this is position 1, and this is position 2. Which means eventually we want to somehow create a new S node here whose value is 42, and then do this hooking up so that we can actually enter it, and this will become the new position 2, whereas the box with 3 in it will be the position 3 now, the node with at position 3. And so this algorithm will work pretty much the same as before, except now we have to account for the sentinel nodes. If we just go back to the original picture, one way to approach this is, we'll split it up just like we did before. Somehow we have to go through and get to position 2, and then do the insertion. Just like before, we'll have to keep track of some current, an arrow pointing to kind of the current node that we're at. So already, just based on what I've seen in the previous question, I can already say that S node is equal to, S node cur is equal to front. Now this gives us a pointer if we go back to the picture that says, alright, here we go. Some of you might be inclined to already say front.next, but remember the front.next may be null. So the approach here is that we want to take position, which in this case would be 2, and make it so that as we go across through the list, the position keeps decrementing until we get to the place right before we want to insert the node. So let's say 2 starts here, and maybe we guess that it'll get smaller as we go. So 2 becomes a 1 once we traverse one node, and then becomes a 0 once we traverse into this node with 2 in it. And if you look at the index versus the position, if we decrement the position in this way, by the time it reaches 0, by the time position gets decremented to 0, we're right exactly where we need to be in order to insert that new node. So first, let's just make sure our code looks like that. We'll say that, again, while position, in this case, has to be bigger than 0, because when we get to 0, we want to be ready to insert into the list. And in this case, because we have this sentinel node in the back here, literally called back, we can say that while cur, which is our arrow, is not equal to back, we want to, just like before, decrement the position, because we said that would get us closer to the answer. And again, we'll do this cur is equal to cur.next, which is saying that as we go along, cur will become different values, as well as us decrementing the position. And so based on the code we have right now, we'll actually go and decrement the position until we get to position is greater than 0, or rather, sorry, position is equal to 0. Let's just see that in action. Like we said here, cur first points to the sentinel front, and position is 2. Because position is greater than 0 and cur.next is not equal to back, cur.next is not equal to back, we want to decrement position, which becomes 1, and then make cur point to this next node, right? Again, the reason why we say cur.next is not equal to back is that we want to make sure that we don't run out of list, right? We don't, in the case that the position is greater than the length of the list, we want to avoid running through and kind of going to the end of the list and even further. And so we just do this again because right now position is still greater than 0 and cur.next is still not equal to back. So we do this again. We move cur and point it to cur.next. And now position is decremented to be 0, which means that we actually exit the while loop here. Now the rest of this code is going to be very similar. In fact, exactly the same as what we did above. Namely, we have to create a new box whose first value is the value we care about, in this case 42, and whose, now that we've gotten to the cur, whose next value points to cur.next, right? It's like this was position 2, so the next points to the old position 2. And then afterwards, when we're going to cross out this arrow, the cur's next arrow, and point it to this new node that we created. And so the way we express this in Python is we say, the way we express this in Java is we say cur.next, right? In discussion I missed the .next part, and this is really important, is equal to a new node, a new S node, whose first value is val and whose second value is the old cur.next. And so there you have it. If you look at this code, it isn't much different than the code we saw before. It's a little bit shorter because we had sentinel nodes. Right now you might be like, sentinel nodes aren't that useful. It makes my code a little bit easier to kind of read, but it's not that, it doesn't reduce the code by that much. If you think about it though, you usually have more than one method for SList. Like maybe you want to insert, but you also want remove, and you also want append, you might want reverse, and all of those different methods may have to have a null check if you don't use sentinel nodes. So a thing to think about in terms of design is that not only do you have to make this one function a little bit cleaner, you could make hopefully a bunch of other methods a little bit cleaner as well by just changing how the data structure, what sort of things it keeps track of, what attributes it has. We'll see this more and more as the class goes on, and that's really what the key behind data structures, the study of data structures are. How do we modify the data structures from kind of the most basic representations of those types of things and give them more attributes, make them store a little bit more information so that the functions that we write and the algorithms we perform on them become a little bit faster or a little bit cleaner or a little bit easier to understand.